So thank you everyone for coming to this session on AI and autonomy in DoD. We've got three presenters coming up today for this session. So please feel free to ask questions as they come up for the first session. And I'll introduce Stuart Harshbarger. Sorry, is that okay? He is the co-founder and chief technology officer of Assured Intelligence at Assured Intelligence LLC. And he's going to be talking to us today about collaborative AI-enabled multi-agent systems. So for those online, please raise your hand in Zoom if you do have a question. We'll handle those as they come up. So,
thank you, sir. So, hello, everyone. I'm Stuart Harshbarger, but I am presenting the material today on behalf of my colleagues on the screen here who couldn't be present. Mike Collins, who's a mathematician researcher at NSA's research directorate, and also the technical director for the NSA Visiting Professors Program, which engages the various service academies and a number of other academic institutions around the country. And Dr. Rosa Heckel, who's a senior system engineer for MITRE Corporation. So between the three of us, we were sort of overseeing and coordinating a broad spectrum of research projects in the general area of raising the resilience of increasingly AI-enabled systems and increasingly collaborative systems. And so that involves a number of different academic partners that there's a little bit of bibliography in the back of the slides I think everybody has as part of their registration package. So with that said, I will try to represent my colleagues in kind of giving an overview here of this broad spectrum of sort of interest in the challenge areas related to, how do we do sort of testing of increasingly AI-enabled systems, whether they're autonomous systems, collaborating in challenging environments, and having reinforcement learning and continuous adaptation in the process. How do you do that? Moving from sort of the model I grew up in doing sort of avionics test and evaluation, where everything was deterministic, and you would take a set of program requirements and you distill those down into representative test regimes, and you would then figure out like what are the number of tests you need to hit as many of those parameters as possible, and then do an analysis about how the system performed under controlled conditions. None of that really applies in the current world. So I'm going to start the conversation for our group here that's presenting, and then I think my other two colleagues are doing a little bit more sort of mature, trying to lay the foundation for program implementation for these test and evaluation methods. So it'll be interesting to see how these points interconnect. All right, so this is just in the background material, but one of the premises of sort of this whole framework is the use of a fairly low computational overhead, consensus-based distributed ledger technology integrated for both mission applications and test and evaluation over the life cycle. And so this slide is, a gratuitous cartoon that I have to do in any of these environments. But it is a point that sort of launched the discussion about, where are the, some of the challenge areas. And so if you start with thinking about one element in the system, like let's just say, that we have this aerial observation system with a computer vision sensor of some modality, some spectrum response that's trying to observe, something in a field, in the battlefield or in an operational scenario. So the part of the premise here is that we're adding multiple platforms, right? So for different reasons, for resilience in one way in case something happens to one of your elements, or perhaps for, one has a thermal sensor, one has a, normal visible domain sensor, others have, radar, and we're starting to look at, what's been the sort of the holy grail of discussion for decades, multi-sensor fusion, but multi-sensor fusion of sensors that are enabled with classifiers that are doing either some sort of machine learning or some sort of collaborative fusion across embedded feature space that might be across more than one modality. So this introduces, of course, in the operational scenario, a lot of different variables, right? So there's certainly people talk about weather and, time of year, foliage, background, whatever the, sort of the other items of, sort of the natural environment are, from sun angle and shading to, whether, we're operating in a forest area or, a desert area. All of these parameters are well known and have been, kind of tried to tackle in various training sets. But also there's these more subtle issues of things like positional accuracy, right, and temporal latency induced resolution or relationships and synchronization. And so if we're trying to fuse information from multiple platforms that all have a little bit of inaccuracy in their actual position and not 100% alignment with regard to their collection of data and their own individual determination of the topic of interest, how do we start to make sense out of that, particularly as the backgrounds may be changing from day to day? And in addition to that, one of the other premises of this work is that these multi-agent sensors are adapting to the environment to try to improve their performance over time. And so if the system is continuously adapting, collaborating in a sort of continuously variable environment and are not deterministic in any way because of the underlying sort of probabilistic nature of AI/ML, how do you do test and evaluation, right? And so I know there's a lot of people in the room that have opinions about that and have very mature documentation and thoughts about it, but that's really the background of this research body. That's what we're trying to do, is trying to figure out how we do that, at the same time raise the resilience of these kinds of collaborative systems, so that if you get into a situation where, it could just be you have a sensor failure or you have, a poorly fit machine learning model and you're getting information back to the sort of consensus-based, commander's intent view perspective, whatever you want to call that. One part of that problem is, can you still operate through a number of errors introduced in the system, either from faults or possibly malicious intent, possibly some sort of contested environment operations like jamming or manipulation of the training data to force the adaptation in a certain way. There's lots of variables. So how could we start to get our arms around the life cycle testing from initial sort of subcomponent design all the way through the life cycle adaptation and use of these systems in real environments? So that's the premise of this discussion. And this is that said in your slide deck that you can reference if it's helpful in future. So this is just a snippet of some of the research partners in this work. They're sort of focused around these topics in gray. So trying to look at the use of computer-assisted reasoning in the area of formal methods. So part of that was coming out of some DARPA programs, internal NSA research activities, and partners, particularly at the Naval Postgraduate School and some other DoD organizations that broader involved in contributing to this effort. This area of resiliency, both in testing and in operational paradigm, is sort of the constant thread through this work. And Vanderbilt University has done a number of interesting projects under this work, looking at, for example, with reinforcement learning and with distributed learning at the individual agent level, then sharing those features across the network in a way that they're not subject to collection and interpretation by a malicious actor, and then trying to discern whether the platform is learning, enriched data from looking at a target from a new angle or under different lighting conditions or a different season that is helpful for long-term performance, or if it's an attempted perturbation of the data in some sort of, gradient kind of attack that would make the models drift off of performance. So in the bibliography, there's some references to some of their papers, and these are all sort of real challenges that the team was thinking about when this sort of concept was resolved. And then that goes from all of the sort of academic baseline. We've been working with the service academies who do these sort of capture the flag kind of competitive operational scenarios with teams of midshipmen from Naval Academy and cadets from West Point and other schools using, increasingly autonomous systems, drones and ground vehicles and surface vessels, and trying to overlay on top of this sort of mock operational scenario, some testing of these kinds of concepts to see, how can we improve the tactical performance from one team to another, but also, how does this really work in a real world situation? So these are some of the topics that we were trying to address here that, I sort of glossed over in the cartoon version of this, but, that any of these systems are going to have non-deterministic behavior, and some of them will, evolve because of adaptation, and there'll probably be some sort of emergent behavior of the collective system that we don't really understand yet and can't really, kind of predict what the sort of full significance of that might be, but it's certainly a factor. The other issue is, we've been starting, with a handful of multi-agents components in these kind of scenarios. So, small swarms, right? So if you think about small swarms increasing in scale to, very large number drone swarms like people have used in all kinds of, artistic demonstrations for the opening of the Olympic opening ceremonies or other kinds of things like that. There's a broad spectrum of scale that we would want to think about. Of course, starting with baby steps, making it work with a handful of sensors first, but then having an architecture that actually grows and doesn't get overcome by tremendous amounts of latency or other kinds of data storage problems in the process. So scalability and complexity from the operational architectural perspective, but also how do we apply that into the testing modalities? Again, the premise is these systems are adapting and learning as we go, and that the environments are changing or are just variable from day to day. Even if you tried to pick the same time of day and the same weather conditions, it's still, everything has a slightly different amount of probabilistic determination from the individual agent perspective, and then from a collective perspective. And then another aspect is we envision that, our DoD systems will want to, coexist and work with collaborating partners. And so by doing that, how do we work together to share data at various levels of, authorities and classification sensitivities? And then if one of those collaborating partners is acting in a nefarious way, how do we remove them from the system? So this is another part of resilience, not so directly related to test and evaluation, but there is a component of making sure that all works that we wanted to consider. So, just to kind of hit on the theme here, the idea is we wanted a system that you could start with at the unit subsystem, that you could basically, during early integration of particular models, for example, this is more, again, AI and machine learning themed, you could do test and evaluation there, collect data that could then expand to, the integrated single agent with all of its individual capabilities, and then become part of a multi-agent system, working together, but then expand that to, a full testing regimen for all of the operational scenarios that system could be applied in, or as many of those as obviously you would be able to do. But you can only do a subset of everything it might encounter. So the idea then is this in situ label would be this provision of constantly collecting data, having some sort of oversight during the operational system in whatever new scenario it's seeing, things like onboard recording of timing variability for like processor operations, looking at anomalies between one platform and another platform that might be doing the same task. So indications of behavior that you could use to lower your sort of trust in that individual component, and then collecting all that information for a more substantial post-processing and sort of follow up, rigorous test and evaluation to improve the system as you go. Yes.
Go back one slide.
Yes.
But especially like to see that. So I'm in the naval world, naval world. Typically, the modeling is an afterthought. The line fire test design, right? We shoot a bunch of missiles, a bunch of testing, and then we put together a bunch of different models and try to recreate that testing. What I'm seeing here is you're actually doing the M&S first, or at least in parallel in front, to then drive how you're going to validate that M&S with live testing. I think what you're saying here.
I think the concept is that they're integral to each other.
Yeah.
Like, modeling simulation helps from an initial perspective, and you have a set of assumptions that drive those constraints. But the idea here is that if you could collect all the information about the individual test scenario or a mission scenario, and then feed that back in the modeling simulation, then the modeling simulation continues to be more robust, and it's a better foundation for building the sort of, system requirements and that sort of.
100% agree. I think investments need to be made as much in M&S as doing modifiers, where I'm going. I think that's
Right.
what you're saying here. It's both.
Yeah, these are not like, this is not a substitution for modeling simulation, right? This is an augmentation of how do you make the data, continuously more robust and representative of the complexity of the world that these systems might encounter.
Thank you.
Does that feedback loop that you just described sort of help the B&B process continually also?
That's the concept here. Again, this is a set of academic research projects that are integrated into like sort of this vision that has to somehow intersect, if it makes sense to people in the room and people that are doing this work in a more, rigorous and formal way, to be integrated into all the other sort of complementary capabilities, the new test range capabilities that can observe, autonomous systems much more robust than old theodolites or onboard recording that, I grew up using, right? So, but then by augmenting all of that together with modeling simulation and increased, performance validation, verification, all of these things, I think are necessary for this kind of very complex, multi-agent environment in the future. And I know there's, a lot of people in the room are very familiar with, the concept of an OODA loop, but I just wanted to put this up here to say, that, we somehow have to come to grips of understanding, I hate to use the term AI explainability, right? This is a kind of a loaded term, but we need to know, at least with some bounds of confidence, what the expected behavior of a system is under, certain environmental conditions, right? That's about the best, sort of concrete deterministic approach I would say is what are the bounds of expected behavior, right? And that's what this red text is at the bottom. But in order to do that, there are all these components that go into that, right? Like what are the variables in position, timing, and guidance? What are the unfolding circumstances or the environmental issues, right? And then what are the internal, delays and feedback between subcomponents of the system that all drive the ultimate, like sort of evidence-based conclusion or recommendation of the system, or possibly its action in a fully autonomous kind of model. So, the part of the purpose of using this ledger approach, and this is again, kind of it's what we would like to characterize as a somewhat low compute, low impact approach, not a blockchain kind of approach or anything like that. But the idea here is we want to know what each individual agent is seeing at all times, and we want to know that in a confident way. So the consensus-based, graph-based ledger allows us to do things like, achieve Byzantine fault tolerance at an individual data element level, so that if you have, 3 elements reporting data at a particular time, the data should match up as long as 2/3 of them are correct, right? So the idea there that we have better confidence in individual data elements that are in the ledger. We also, the time synchronicity of when the data was transmitted and received within an individual element is critical. So that's something a test range can't really see, right? You can know when command was sent, and you can know when the agent reacted to it. And if you have good correlated time synchronicity, you can know, what timestamp is on the reception of the command. But you can't see the full ordering of which sub-element saw it at what time, and how sort of traceable the chronological history of command and control and response are back into the process. So that's another mechanism that sort of extends from this ledger approach. And then the other approach is, from an operation perspective, we want to, make the system as decentralized as possible, ideally fully decentralized. We're looking, with Vanderbilt models of decentralized learning, in a much more theoretical future vision of things. But the idea there is that, you increase the resilience by not having a single point of failure, and the number of nodes that could have some sort of fault failure or malicious activity, is dependent upon the number of nodes that are engaged in a particular operation, up to about 1/3 if in this ideal by default tolerant case. All right, so I think here I don't want to save some time for questions, but this sort of goes back to that question of sort of about, modeling and simulation, like, by having this ledger information during test and evaluation, during operational scenarios, during experimentation, this all feeds into, this set of confidence in data that's more, representative of the real world, but also, we know that it's synchronized. We have some increased confidence that the individual parameters were received accurately and there weren't bit flips for some reason in the process. And then we want to, make all that data accessible to, the development teams and the test and evaluation teams, so that it's a continuous sort of process of looking for, did an anomalous behavior occur in an operational scenario that we hadn't seen before or hadn't predicted, sort of this sort of emergent behavior from a cybersecurity or a systems resilience perspective, not necessarily a functional capability perspective. And then this is just sort of the concept of these things, like, in terms of anomaly detection, there's a representative snapshot of what the data ledger might look like. But some of these elements might also be, like I was saying, onboard, sort of tiny machine learning or, statistical based monitoring processes that could provide, a level of confidence. And, is the individual agent processor running at a pattern that's representative of the original sort of bench testing and assumptions, or is it consistent with the data from across, all the other elements that are doing similar kinds of tasks at that point in time? And so that's, sort of, the idea is that you would apply other machine learning and AI technologies, large data analysis activities offline to do really robust test and evaluation of this ledger data for the purposes that, it adds value to. So anyway, that's sort of the snapshot view here in the time we have. So I know we had one question going forward, but did it save time for questions from online, or does anybody else in the room have any thoughts? And more particularly, I'm interested in, and I'm sure my colleagues are interested in, what components of this are already being integrated into, sort of the recommendation papers for testing, autonomous systems and collaborative systems, and, what gaps do you see in the test and evaluation, regiment that this approach, might contribute to, and then we could connect you, and follow up to, some of the academic partners that have been exploring these different methods and looking at all the issues. There's practical issues about latency, particularly as the system scales, and trying to figure out maybe latency doesn't matter as much for the real-time recording. And then if we do post-processing for a T&E purpose, maybe we can sort of build back out all that latency and it doesn't affect. But if it's a operational scenario and you want to do, make a decision about the next mission operation based on the collective data, latency certainly matters, right? So you're trying to figure out where are the gaps and to what application space they apply. So, anyway, thank you for your time on that. Questions?
One comment. I think a gap that I see as a DOT needing an action officer is a lack of the infrastructure for the M&S testbed piece, where you can create that LVC environment to do this type of testing, to then port it into the real world and run that test, and then go back and validate. I don't see, and again, it may be happening in pockets of excellence, but from a 3 to 5 year timeline, you're looking at major ACAT attempts that will utilize autonomy. I don't see that kind of test bed infrastructure, a place that we could pull from maybe tools that you have or other folks have to create that virtual environment. I think that's what I see kind of missing. I see talk about it, but I don't see actual resources in that environment being built. A lot of the testing that I've seen, Jen probably better than I, is we're going to test it all in real world. Right? We have no place to go play. We're just going to do all of that probabilistic, hundreds of hours of testing, which we know will never really happen. You don't have enough time and money to do it. So I think there needs to be investments there and access the technology that can already exist by some agencies to help the services, the acquisition community actually build that infrastructure.
No, that's a really good point. There's another aspect of this work that in this sort of formal methods for, requirements definition. The work for Naval Postgraduate School is around part of it is around this platform called Monterey Phoenix. Has anybody in the room ever heard of Monterey Phoenix? It's sort of a, computer assisted system engineering tool, but the idea is to sort of validate, your modeling simulation requirements or other sort of operational requirements, as a way of using this sort of computer process and a mathematical sort of extraction of information from different threads throughout that process to make sure that as you do modeling simulation or as you make assumptions about, what would be the requirements to achieve a particular, operational or mission system outcome, that, whether something logically missing in that sort of evaluation. So I see it as sort of a supplement to, the fact that, a lot of these systems your requirements are developed by teams that are somewhat isolated from each other. They come together, at the program level for a design review and a go decision. But, this is maybe a missing piece of making sure that if we're going to use modeling simulation and we only have a limited amount of funding to, have the insights to that, to build that up in a robust way, and only a limited amount of time and dollars to do the full operational testing. We want to make sure we do that in the most effective way possible. And so that's a tool that sort of leans into, doesn't solve everything, just another tool in the toolbox to try to improve the validity of your assumptions.
Yeah, tag onto that and say if there are thoughts on how multiple programs, like usually a single program, especially smaller programs like MTAs that are trying to use autonomy, aren't going to have the resources of the bigger programs. But if there are kind of shared missions, if there's multiple mine countermeasures programs that could use some shared test bed or the unmanned ships, something like that, if there are kind of ways that academia and industry can help us understand how to pool some of those resources to meet kind of a joint mission need, that could be a very useful thing. And another thing that I've been thinking about more is we have to start the instrumentation for operational tests a lot. So it can be production representative, whether it's to secure it or remove kind of test instrumentation to get us some data. So I think it would be great to keep a lot of that instrumentation on board. But some considerations in that vein, I think, would also be helpful for the community.
No, that's great. So that sort of is related to something I've been thinking about that's really not part of this talk or isn't really very well formed yet. But, I just had a briefing last week at an exercise up at West Point from somebody who's providing technical support in Ukraine and talking about, just the rapid adoption and utilization, as we've all seen on the news in various places, of, commercial technologies for these, kind of novel systems. And so wouldn't it be great if we had the ability to throw a little payload and collect some of that information as part of, providing insight to, our next generation of system design, our own test and evaluation of, more complex system. But this whole cycle of hurry up offense and defense and, in context is something that, we've all sort of probably been part of, little projects that responded to an immediate action and bypassed all the formal methods and all the sort of, verification validation just to get something done. And this might be a way of filling that gap a little bit as well, but, part of the conversation. So thanks so much. End it off.